Alright, because I'm too lazy to type all this up, probably easiest just to put this into a Maple worksheet and provide it to you directly, but I thought I would at least walk through the procedure of how I went through and used Maple to form my Taylor series. We looked at a particular function. I'm not even quite sure what function we used in class, but let me just do as a simple demonstration the function sine of x, and let us develop the Taylor series centered at a certain point. Now, I demonstrated in class that there were two ways to go about this. One was to basically manufacture this yourself. So this first technique is what I refer to as the expression technique, and that's where we have to use the substitute command in order to create our Taylor series centered at a given point. So let's say we want to center at the value x is equal to, for example, 8. I think that was the number that we used before. We are using a different function. We'll use the same center. Why not? So we'll call df the derivative of our function, our function f evaluated at x. And then ddf I'm going to call my second derivative. Remember, with the derivative command diff, you are able to take higher derivatives by simply repeating which variable you want to take the derivative with respect to. Now, if I only want to build a quadratic polynomial, that is a Taylor polynomial of degree 2, I only have to go up with the second derivative, and now what I can write is that my t sub 2, representing my quadratic Taylor polynomial, will be, if I substitute my center into the original f, plus if I substitute my center into the original f, times x minus 8, plus the substitute, by the way, not into my original, or into my derivative there, and then substitute x equals 8 into my second derivative. Divide that by the 2 factorial, because we're on the second derivative, times x minus 8. If I can type a minus, and square it. And there it is. And so if you were to take and plot, oh, by the way, I was able to simplify that further if you would rather see it in simplified form, that is expanded all the way out. You could even eval f the result there and have a very specific form for your Taylor polynomial. And if you were to plot, say, t2 and f on the same curve from, say, x goes from negative, or from 7 to 9, you would see that in fact these two curves are very close. Oh, sorry, t minus 2, here's my mistake, so t sub 2. And so near this point the two curves are somewhat similar, but not greatly similar. Let's double check and make sure that I did not make any mistakes. Oh, there's my mistake right there. My second derivative was evaluated at 3 instead of 8. I expected the curves to be closer than that, so we see that we made a mistake at that point. Follow through and you see you get a much closer picture of that curve. But the further away you get from the point 8, the worse off you are. The second approach was to use a function for f, and in fact I'm going to call this ff, so as to not confuse it with the function above, and then the derivative of that function would be the d of ff, and then dff would be the, let's call it ddff for the second derivative, would be d, remember where the notation for the second derivative in function form is d with the double at symbol, 2 ff, and there you have it. And so what we can actually do in this case is simply say that t sub 2 now is equal to ff at 8 plus dff at 8 times x minus 8. By the way, I want to create this as a function to be consistent. And then plus ddff at 8 divided by 2 times x minus 8 squared. you can evaluate at any given point. And thus we could plot it in the similar manner, except now treating t sub 2 as a function of x and f as a function of x from x equals 7 to 9 will produce the same picture that we saw before. And don't forget that still I haven't taken the time to investigate how to get the higher order terms off, but in the Taylor command, if you were to simply say t sub 2 is equal to the is assigned to Taylor of f at x equals 8, let's go 3 terms, you actually see the same. First 3 terms represents the Taylor polynomial of degree 2. Then you have the higher order terms following that. And so there is a technique that I am going to investigate and will provide to you in class hopefully next time, but it may be something later on, as to how to use the Taylor command to strip off the last term of that particular output. Alright, there you go. That's all I have to say about this. I'm going to save this, and you will be able to download this as well. It'll be referred to as the TaylorSeries example. Alright, thank you very much, and goodbye.